deposition system, electron beam, technique, sol gel technique, okay, ball milling, and stripped heavy iron techniques. These are some of the techniques which are used for this much. So I will go very quickly.
सर का शायद कनेक्शन लॉस्ट हो गई। उन्होंने ज्वाइन कर लिया था।
हाँ डॉक्टर साहब, ये थोड़ा सा लिंक में प्रॉब्लम आ रही है। मेरी आवाज आ रही है ना?
अब आ रही है सर। प्लीज सर स्क्रीन दोबारा शेयर कर दीजिए सर।
हाँ एक्चुअली मैं हाँ स्क्रीन शेयर हो रही है?
यस सर।
ओके ओके। हाँ सो these are some of the techniques. Basically, I have already told you there are two methods. One is physical method and other one is the chemical methods. And under the physical methods category, two types of things are there. One is under the vacuum and other one is under the sputtering category. In the vacuum category, basically these are resistive heating, flash operation technique, electron beam operation, laser operation, arc operation, and radio frequency techniques are there. Under the sputtering techniques, we have glow discharge, DC sputtering system, triode sputtering, getter sputtering, radio frequency RF sputtering, magnetron sputtering, phase target sputtering, and ion beam sputtering. Under the chemical methods category, there are two, again, it is divided into two subcategories. One is gas phase and the other one is liquid phase. In the gas phase category, the techniques are chemical vapor deposition, laser chemical vapor deposition, photochemical vapor deposition, plasma enhanced chemical vapor deposition, metal organochemical vapor deposition. And under the liquid phase, these are electrodeposition, chemical bath deposition, successive ion layer adsorption and reaction, that is known as also known as CILAR in short, electroless deposition, spray pyrolysis, liquid phase epitaxy, and sol gel process. So these are the different techniques which are coming under the two categories, that is physical and chemical methods. So I will go quickly.
अशोक सर।
अशोक, उनका माइक ऑफ हो गया।
हाँ
जी
मेरे ख्याल से फिर से प्रॉब्लम आ गई शायद कुछ।
हाँ यस, स्लाइड्स मूव कर रहे हैं।
हाँ स्लाइड मूव कर रहे सर। हाँ बीच में आपका म्यूट हो गया।
वो कुछ
माइक ऑफ हो गया था सर।
नहीं, माइक हमने ऑफ किया था बिकॉज स्लाइड्स वर नॉट मूविंग।
ओके
तो माइक तो हमने ऑफ किया हुआ था उस समय। देन द रेजिस्टिव हीटिंग, basically it is also known as a thermal evaporation type of thing. Here we are using a boat, and it can be done inside a vacuum chamber. Okay, and the films, the material is melted at a high temperature, which can be heated by flowing a high current inside a vacuum chamber. And all of us are knowing that why a vacuum is required, because otherwise what will happen in that case? The atoms which will be evaporated, they will not reach to the substrate, because the mean free path will be less, as these molecules or atoms, they will collide with the atmospheric gases and all those things. Okay, so that's why we need a vacuum here. So advantages of this technique is normally these films are very pure in the form, and highly uniform films can be deposited on the substrates, and normally these substrates are the glass substrates or carbonic 7059, something like that. The disadvantage, every technique has certain advantages as well as disadvantages also. So the disadvantage is this is a very high temperature process. So what will happen, sometimes the molecules, they are broken, okay, and the composition may change. Okay, so that is a basic problem, and you need a ultra high vacuum, and cost of the system is high. So these are the disadvantages. Now the next one is the flash evaporation technique. So it is basically partial or total vaporization that occurs when a saturated liquid stream of that material undergoes a reduction in pressure by passing through a throttling valve. Throttling valve means we can there is a valve through which we can control. So this may be valve also, or this may be some mass flow controller and all those things. Okay, and this process or technique, you can say that is one of the simplest technique which are available. The next one is the electron beam evaporation process. In this process, we are using the energy of the electron beams, which are generated from the hot filament, or you can say the electron gun. Okay, and in this case, high voltage is applied between the filament and the or to accelerate these liberated electrons towards the crucible where the material is kept. Okay, and when this electron beam will hit the material which you have kept in a crucible, then the molecules will come out, or you can say the material will evaporate, and you will get a deposition of the film at a substrate which has been kept at some distance. Okay, so this is electron beam evaporation. Then the next method is basically the laser ablation method. This is a very good method, and the advantage of this method is you can get a very uniform deposition of the films, and number one, and number two, the composition of the material that will remain same on the film formation also. Okay, and normally single wall nanotubes or multi-wall nanotube or metal particles, those can be used for the deposition of such type of these materials, where the melting point of the material is high as compared to the other materials, and the materials which cannot be deposited by the other techniques like flash evaporation or thermal evaporation or electron beam also. Okay, and this is a setup you can see here. Here a laser beam is there and the gas is flowing. Okay, so what will happen in that case? The gas will be dissociated into its form, and in that case what will happen? The gas that will hit the target and the materials will come out from the target. Suppose we have a graphite target here, so what will happen? The carbon material will come out, and under the certain conditions, okay, you can get the single wall nanotube of carbon or some other carbon materials also. The advantage of this technique is it has a good diameter control of the carbon nanotubes, fewer defects are there, and one will get the pure product. And disadvantage, all of us are knowing the cost of the laser is very high. So this is very expensive because of laser and high powered equipment which you are using in this technique. The next one, that is the arc discharge method. Basically, it is a physical method for the making the nanomaterial synthesis. And here we are using the inert atmosphere. So for that purposes, we can use the argon gas or helium gas also. Normally we are using the argon gas because that gas is easily available. Okay. And in the arc discharge technique, basically it is an electrical breakdown of a gas which produces an ongoing plasma discharge. Okay. And normally we are using this method for the making the carbon nanotubes or boron nanotubes, gallium nitride boron nanotubes, and all those things. Okay, you can see there's the schematic diagram of this one. There are two electrodes, one is cathode and another one is anode. And when we apply very high electric field, what will happen? An arc discharge is produced and one can get the deposition. Okay, so what will happen? Under these conditions, what will happen? Some of the carbon which is evaporated from the anode recondenses hard cylindrical deposit on the cathode raj. And the advantage of this technique is that the production of high quality carbon nanotube we can get. Disadvantage, it is a high temperature. All of us are knowing that when the discharge is produced, very high temperature is produced. So it is difficult to control when you have started the arc discharge in this system. That is the major disadvantage. You do not have very much control in this technique. Molecular beam epitaxy, this is a very good technique, and it is basically a technique for the epitaxial growth by the interaction of one or more molecular atomic beams which occur on the surface of a heated crystalline substrate. And we are using a very high ultra vacuum, which is of the order of 10 to the power minus 8 to 10 to the power minus 12 torr, which can be achieved with a turbomolecular pumps or so. Okay, the most important aspect of this molecular beam epitaxy technique, that is the deposition rate, which is typically less than 3000 nanometer per hour, that allows the films to grow epitaxially. The absence of carrier gas as well as the ultra high vacuum environment that will produce the highest purity of the grown films which you are depositing here. This is a system you can see here. There are different attachments and okay, so there are different attachment as well as online measurements you can also do inside this chamber. So then the next one is the sputtering category, and all of us are knowing that under the sputtering category, there are basically 4 types of sputtering techniques are there. One is DC sputtering, then triode sputtering, RF sputtering, and magnetron sputtering. I will go quickly to here. In the DC sputtering system, basically we have 2 electrodes. One is known as cathode and other one is anode. And one electrode we are making, we are putting a target material which you want to deposit here. At the other end, on the another electrode, we are putting the substrate where you want to deposit the material. Okay, and you can see in the picture the substrate holder, anode and cathode is there. We are putting the target on the cathode, and on the anode we are putting the substrate material. Okay, and the argon gas is inserted inside the chamber with the help of the mass flow controller. And when a field is applied between these 2 electrodes, what will happen? Argon ions, they will bombard the target surface, and from there atoms or molecules, they will come out. The advantage of this technique, it is very easy to control, and it is a low cost option is also there. And normally it is used for the deposition of the metal. Okay, metallic films also. Disadvantage is that it is the non-conducting dielectric materials, or you can say the materials which have high resistivity. These may be high resistive semiconductors or insulators also. In such cases, what will happen? In the non-conducting dielectric insulating materials take on a charge over time, which can result in quality issues. Okay, and we will get very less deposition if the material is highly resistive also. Then the triode sputtering system, basically it comprises a plasma confining enclosure, including a cathode at one end and anode at the other end, which is similar to the DC sputtering system. But here we are putting a central plasma supporting system. Okay. And you can see in the diagram, okay, target is capped, substrate is there, and we are putting a sealed inside this much, which can act like a triode. Okay, the deposition pressure which we are using in this system, that is typically of the order of -3 to -5 torr or so, and the temperature is around 100 to 150 degrees centigrade. The advantage of this system is triode sputtering system is we need a low deposition pressure, relatively high deposition rate we can achieve as compared to the DC sputtering system, and low substrate temperature is also we can use. The disadvantage is we are getting non-uniform coating over large surface area. Means if the surface area is very high, in that case there may be a possibility that the uniformity issue will be there. Non-uniform coating may be there at some places. The coating is uniform, and at the other uniform means thicknesses, some different thicknesses may be there as we are reaching outward to the substrate also. Complexity and difficulties of scaling is there, and shorter filament life which we are using for this purpose. Those are the disadvantages. Then the radio frequency sputtering system, basically this type of system is used when we are going to deposit for the insulating or highly resistive materials, which cannot be done either with the DC sputtering or with the triode sputtering. Okay, so in this case, in the radio frequency sputtering system, this is the technique involved in alternating the electrical potential. Normally we are using the radio frequency that is 13.56 megahertz or so. So alternating the electrical potential of the current in the vacuum environment at reduced frequencies to avoid a charge building which is taking place in the DC sputtering system on certain types of sputtering target materials, which over time can result in arcing into the plasma, that spews droplets, creating quality control issues on the thin films. Advantages of this technique is it can sustain plasma throughout the chamber at a lower pressure, that is of the order of 1 to 15 millitorr or so, and it prevents a charge buildup on the target or coating material. The disadvantage is that deposition rates are considerably slow, and it requires much higher voltage in that case. Then the next one is the magnetron sputtering system. It is basically a plasma vapor deposition process where the plasma is created and the positively charged ions from the plasma, those are accelerated by an electrical field which is superimposed on the negatively charged electrode, or you can say the target. Okay, the positive ions which are accelerated by potentials ranging from a few hundred to a few thousand electron volts, and they will strike the negative electrodes with sufficient force to dislodge and eject atoms from the target. Now these atoms which are ejected, they ejected in a typical line of sight cosine distribution from the face of the target, and they will condense on surfaces which are placed in proximity to the magnetron sputtering cathode. So we are using a magnetron source here. You can see this is a schematic diagram. Okay, here we have used a magnetron source through which we can apply the magnetic field also, which can control the plasma which is positively charged in that case. The advantage of this system, we can achieve the high deposition rate, reducing electron bombardment of substrate which is taking place, extending the operating vacuum range and ability to operate at lower pressure. However, the disadvantage is that the non-uniform removal of particles from the target results in non-uniform films on the substrate. Because one thing we must remember that uniformity and the repeatability, these are the two issues whenever we are going to deposit the thin films. Because if you are having the non-uniformity, or you can say uniformity, uniformity is not there, in that case, what will happen? Then we will have a lot of defects which are created in the on the films, and these defects, they are playing a major role for whenever you are going for the fabrication of the devices. Okay, and erosion track in the target that leads to poor efficiency of sputtering, which yields sputtering yield versus target volume compared to non-magnetron sputtering systems also. Then the next one we have discussed till now, physical vapor depositions. Now we come across the chemical vapor deposition techniques, and as its name, chemical is there. So in this case, there is a precursor gas which are inserted into a chamber which contains one or more heated objects to be coated. Okay, and chemical reactions, those are taking place inside the chamber. Okay, so there are different types of systems are there. One is thermal CVD, then other one is plasma enhanced CVD, that is known as PCVD, and the low pressure CVD, that is LPCVD system is there. In a typical CVD process, the substrate is exposed to one or more volatile precursors, and these precursors, they will react or decompose on the substrate surface to produce the desired deposit which we are interested to deposit on a substrate. These volatile byproducts are also produced and are removed by gas flow through the reaction chamber. In thermal CVD system, you can see this is a system schematic diagram. Here we have a furnace, quartz furnace is there, and there is a quartz tube because quartz can sustain at a high temperature, and the temperature range may be from 750 to 1200 degrees centigrade or so, and an evacuation is done to remove the unwanted gases which are coming inside the chamber. The gas manifold system is there through which you can flow the gas or you can send the gas through the mass flow controllers. And suppose you want to deposit carbon here, some carbon compound, maybe carbon nanotubes or fluorine or something else. So in that case, you are supposed to have the gas of carbon. So this may be styrene, this may be methane or ethane or some other gas which is having carbon material. Okay, so the limitation of this technique is that your material must be in the gaseous phase, and these gases can be sent through a carrier gas, maybe hydrogen or some hydrogen we are using because hydrogen is not reacting with the carbon material in a great extent also, and this hydrogen can be removed if you will annihilate a higher temperature also. So that is the actual. Then the plasma enhanced CVD system, basically this system uses an RF induced glow discharge where that energy transfer into the reactant gases that is taking place. These two types of these systems are there. One is parallel plate and other one is the Hall wall type. In the parallel plate, as its name, the reaction chamber is cylindrical and constructed of aluminum coated stainless steel. Okay, and these are the aluminum electrodes which have been cut on top and bottom. Okay, and sample which you want to make that lie on the grounded bottom electrodes. You can see these are the wafers. Okay, and then the RF electric field is applied to the top electrode which creates a glow discharge between the two plates. Gases flow readily through the discharge. Okay, and due to which what will happen, a discharge is produced and one can get the deposition. Advantages of this technique is this is a low temperature deposition, and disadvantage is that the wafer must be loaded and unloaded individually, and there may be a chance of contamination when you will open the chamber for the loading the wafers in this system. Hot wall type, basically here the reaction is taking place in a quartz tube which is heated by a furnace. A furnace is there, and this furnace may be with different zones also. Different zones means at some particular length temperature is 1, then in the middle temperature may be different, and at the end the temperature may be again different. So different temperature zones are there. So that's why we are using 3-zone furnaces most of the time. The electrode assembly that contains long graphite or aluminum slabs to support the wafers here, and alternating slabs those are connected to power supply to generate discharge in the space between the electrodes. And okay, advantage of this technique is you will get the uniform material deposition on the substrate also, and large number of wafers can be deposited using this technique. However, the disadvantage is that the contamination while loading and unloading that will take place in this technique. Low pressure CVD, here again the same type of system is there. That is the we have a quartz tube which is heated by a 3-zone furnace. Okay, and the gas which you are introducing inside this chamber from one end, that can be pumped out from the other end. Okay, and here the wafers which you are placing inside the chamber, those are vertically, or you can say perpendicular to the gas flow. And for that purpose we are using a quartz holder where we can put the wafers. Advantage of this technique is through this technique we can get the excellent purity, comfortable step coverage, large wafer capacity. However, the disadvantage is it requires a high temperature and the low deposition rates. Okay, then the chemical bed deposition technique, CBD in short we are knowing, it is basically a wet process also we can say, where we are using the liquid materials which you want to deposit here. Okay, so this process is done in basically 3 steps which you can see in the schematic diagram of the system. The first step is the creation of atomic, molecular or ionic species. In the second step, the transport of these species through a medium, and the third one, that is the condensation of the species that is taking place. Okay, and CVD, that is basically depend on the principle, it works on the principle of the controlled precipitation of the desired compound from a solution of its constituents. Okay, the precipitation is observed in solution only when the ionic product exceeds the solubility product. This is a simple chemistry of the 11th and 12th standard which is taking place inside this. Okay, then the sol gel method, that is another technique, chemical route is there, wet process. Okay, it is a chemical solution process which is used to make ceramic and glass materials in the form of thin films, fibers or powders, whatever is there. And basically there are 2 names as there, one is sol and other one is the gel. So sol is basically a colloidal, or you can say that the dispersed phase is so small that the gravitational forces do not exist, only van der Waals forces and surface charges are present. Okay, or in other words you can also say the molecular suspension of solid particles of ions in a solvent, that is known as a sol. However, the gel, it is basically, it is a semi-rigid mass which forms when the solvent from the sol begins to evaporate and particles or ions left behind the begin to join together in a continuous network. So this is a thing by we can see here. Okay, then the CILAR, that is successive ion by ion deposition process, CILAR method, it is basically also the same type of thing, only some modification has been done in the chemical bar deposition. So here in the CILAR method, it is basically based on the adsorption and reaction of the ions from the solutions and rinsing between the every immersion with distilled water to avoid homogeneous precipitation in the solution. So you can see here, you can see basically the adsorption, that is the cations which are present in the precursor solutions, those are adsorbed on the surface of the substrate. This is first step. Then we are doing the rinsing, that is known as first rinsing. So what will happen during the first rinsing, loosely adsorbed ions, those are rinsed away from the diffusion layer. Then the next one, that is the reaction. Okay, so third step, reaction. So the anions from the anionic precursor solutions are introduced to the system Due to the low solubility of ions reaction between cation and anion takes place, leading to formation of solid phase over the substrate. And then again the rinsing is done, second rinsing, that is known as where the excess and unreacted species and the reaction byproduct from the diffusion layers, those can be reduced. So basically it is a 4-step process: adsorption, first rinsing, reaction, and the second reaction. Okay, then the spin coating technique, it is a very simple things. Okay, the basic principle, that is centrifugal force, that centripetal force that is used. Okay, so here in this process, solution is spread evenly over a surface using centripetal force, which is responsible for the spread of liquid across the wafer. Okay, it results in a relatively uniform thin films of a specific thickness. Whatever thickness you need, that can be achieved with this much. And it is an important way of coating thin films in the microelectronic industry. Just like if you want to make the photolithography material resins or all those things, and then this technique is used. Or in the MEMS devices also, it is used for that purpose. So here you can see you are putting your substrate on a rotor which is connected with a very high speed motor. Okay, and then you are applying the solvent solutions, and what will happen due to the centripetal force, the molecules of the liquid drops, they will try to come out and uniformly distributed on the substrate. So that thing is used here. Then the electrodeposition, basically it is also known as electroplating, and nowadays all of us are knowing artificial jewelry which is available in the market, that is made with the help of the electroplating and all those things. So simple principle is there. We have two electrodes. One is known as the working electrode and the other one is counter electrode, and in between there is a reference electrode we are using here. The solution which we want to use for making the films, that we are putting in a beaker, and then we are applying a electric field. What will happen due to the electrolysis and all those chemical reactions, we can get deposited the material. Okay, in that one. Then the technique is pyrolysis. This is basically it is the aerosol process that atomizes a solution and heats the droplets to produce solid particles. And atomization, all of us knowing, that is the production of droplets and their dispersion into the gas. However, the aerosol, that is defined as a suspension of solid or liquid particles in a gas. That is, so this is a you can say a schematic diagram of such type of system. You can see here diffusion dryer is there, thermolysis reactor is there, sintering furnace is there, and then atomizer and carrier gases, that is there. The carrier gas is sent through the mass flow controller and all those things we can get. The deposition. The advantage of this technique, it does not require high quality targets or substrates. It does not require very ultra high vacuum system, and it continuously produces the material. Okay. Then the next one, that is liquid phase epitaxy. It is a method to grow semiconductor crystal layers from the melt on solid substrates, which happens at temperatures well below the melting point of the deposited semiconductor. And the semiconductor is dissolved in the melt of another material. So at certain conditions which are close to the equilibrium between the dissolution and deposition of the semiconductor crystal on the substrate is slowly and uniform. This is a system which is used. The advantage is this is basically a near equilibrium growth, excellent crystal quality you can achieve, inexpensive and fast. The disadvantage of this technique is difficult to scale up for production and poor dimensional control. So this is another technique that is known as Langmuir Blodgett film. Okay, it is a nanostructure system which form when Langmuir film or Langmuir monolayers are transferred from the liquid gas interface to solid supports during the vertical passage of the support through the monolayers. And these films can contain one or more monolayers of an organic materials deposited from the surface of a liquid onto a solid by immersing the solid substrate into the liquid which you have kept in that setup. Okay, this thick okay, you can see this is a system here where one can deposit. Here is a dipper is there through which you can control the speed of the substrate which can be immersed inside the liquid solution also. The substrates are connected with the substrate holder and microbalance is there, then moving barriers in there and all those things. And this is a computer control system through which you can control the speed of the dipping, you can say, inside the liquid. Then these are all the techniques which we have discussed. Now the materials which have been deposited on the substrate by different techniques, I can show you some of the results. So this is a transmission electron microscopy of a cadmium selenide thin films which can be deposited using the physical vapor deposition system in the system. And you can see these are having the spherical shapes and all those things. This is another material basically. This is another material. Basically, these are the silver nanocrystals, silver polyvinyl propylene polymers, silver nanocomposites, those have been formed. And here you can see, as we have increased the molecular weight of PVP, what will happen? The shape of the particles, nanoparticles, that is changing from hexagonal to needle type of shape, you can see here. Then this is another nanocomposite. This is a cadmium sulfide, cadmium selenide nanocomposite material. And here we can see that the bronze type of structure we are getting here. Then the next one, that is the cadmium sulfide. Here this cadmium sulfide, when it has been dispersed in the PVA matrix, then we are getting the spherical shape. Okay, this is this much, and this is another one. This is a core cell structure. Okay, and you can see there is a core of one material and the cell of the another material, which you can see here. Then now we come across the techniques which we will discuss now. So we have basically divide our talk, this portion, into different topics. First, I will go very quickly the material preparation which I have taken, then the characterization tools. These are optical, photoluminescence technique, electrical measurements, and time of flight experiment which we have designed and fabricated in our laboratories, and single slit photo grating experiment, thermally stimulated current measurements, constant photocurrent measurements. All these techniques I will discuss, which is used for the determination of the different transport parameters in the laboratory. And if the time permit, I will discuss some doping effects. Otherwise, I will skip this part here. So the material, because we need a very high purity material. So let us take the example here. One, that is cadmium selenide, whose composition is 35 and 65, and then we have done the doping with different metals like copper, zinc, indium, tin, lead, and silver. These have been kept inside a quartz tube which has been vacuum sealed here. Okay, and then these quad ampoules, where you have kept these materials in a desired atomic percentages, they have been kept inside a furnace where the rocking arrangement is there for 24 hours, or sometimes it is more than that also. And after, so that the homogeneous mixing can take place. And then these are cones in the liquid nitrogen or ice bath, depends upon the cooling rate, and that quenching is done, and then we are getting our samples after working the ampoules in the form of bulk. Okay, ingot, some ingot. Then these are crushed and these are used for the deposition of the film. This is the actual film which we have deposited using the physical vapor deposition technique. The glass substrate which we have taken, that is Corning 7059 glass. As we know, Corning is the name of the company, American company. Dow Corning, all of us are knowing. And 7059, that is a particular number of the glass, and the advantage of this glass, it is basically the alkali free. So very high resistive glass substrate is there, because the current which we are going to measure uh, by depositing these materials on the glass film, that is very low. So what will happen if the substrate material that does not have high resistivity, then there may be a possibility that the current may pass through the substrate also. So just to avoid for that, we are taking the alkali free glasses, and for that purpose we have used the Corning 7059 glass here. And for the electrical measurements, sometimes we have used the pre-deposited thick indium metal, or sometimes we are doing the same process after depositing, that is known as the post deposition. We are using the indium metal. We have tried with different metals like silver, indium, and gold, okay, for making the contacts. So our purpose to do this much, that the diffusion of these metals when you are applying the electric field, or the temperature that does not go inside the material of the thin in the thin films. Okay, so just to avoid that much, we have taken the indium, because indium we have measured in our laboratory that which metal goes fast as compared to other ones. So what we have found that indium, the diffusion of the indium metal is negligible, you can say, for a certain day, few days or so, where the measurements are done. The thickness of the film which we have measured, that is around 165 nanometer or so. So this is, first of all, whenever we are making any material inside the laboratory, the first thing one should see what type of structural thing that material has, whether it is crystalline, non-crystalline, or nanocrystalline, what is there. So here you can see the X-ray spectra which we have taken, and we have obtained the hexagonal structure. And okay, so these are the three spectra of the XRD. One is without any doping, and the other one is copper dope, that is 1% and 5%. We have done for other concentrations or also, but just I am showing one is the low concentration and other one is the high concentration. So for that purpose we have chosen 1% and 5% here. So here we have seen basically when it is undoped material, we are getting just one peak, that is plane 100 is there. Hexagonal or giant crystal structure, we have obtained a peak at 23.4 degree also. However, when we have doped it, we are getting two or more than two peaks in that case. In copper 1, we are getting 100 and 002 peaks. However, in the other case, we are getting the other hexagonal structure is copper selenide. So one is for cadmium selenide, that is 100 plane and 002 plane. However, the other peaks that we are getting at 29.7 degree and 41.1 degree, 103 plane and 106 plane, which is coming due to the copper selenide. The average crystallite size which we have obtained in case of undope, that is around 12 nanometer or so, and after the copper doping, it is 31 nanometer and 44 nanometer. So it means the crystallite size increases as we are doping with copper. These are the you can say transmission electron microtm spectra. Okay, for cadmium selenide with copper 1% doping, and cadmium selenide with copper 5% doping, which you can say. In the right side, we have the scanning electron microscopy, same spectra, and we can see the very good uniformity which we are getting in that case, and also the composition, whether whatever you are mixing, that is copper 1% or 5%, whether we are getting the same composition or not, that we can see from the table here. Then the optical measurements, all of us are knowing that the optical absorption, that is controlled by the optical transitions. And you can see this is a schematic diagram, basically three things are, we have divided our spectra in three different forms, in three different regions that has been designated as region A, B, and C. So in region A, you can see the transition is taking place between tail to tail. In region B, the transition is taking place from tail to extended states. And in this case, the absorption coefficient, which we are saying as alpha, that follows the Urbach rule. However, in the region C, where the transition is taking place from extended to extended states, in that case, the alpha follows the Tox relation. Okay, and these are some of the transmittance spectra from where we have calculated the energy band gap of this material. We can see here, okay, so we can see here the band gap of the thin films which we have deposited, that decreases continuously as we are increasing the concentration of copper. Initially it was 2.25 electron volt, and then it decreases to 2.17 electron volt after copper 1% doping, and further at copper 5% we are getting 2.02 electron volt or so. This is the photoluminescence spectra of those films. Okay, and here we can see we are getting an emission band at 584 nanometer or so, which is basically, that is the excitonic emission, and the band at 531 nanometer and 487 nanometers, that is due to the deep trap state emission that is taking place. Okay, now emission peak at 767, you can say, in the other case, that is in the case of copper doped, that is coming due to the copper related luminescence centers which has been created after the copper doping, and photoluminescence emission, that is quenched states are coming out. Okay, as compared to the cadmium selenite peaks, and band edge emission peak, that is asymmetric, which is due to the transitions involving impurity donors and surface trap states which are present in the films of these materials. And if you can see from the schematic energy level diagram, you can understand the things. Okay, the red shift after doping that is taking place, that is due to the wider size distribution of nanoparticles. Okay, and at 5% copper, emission dominates due to the copper levels which are introduced after the copper doping inside the materials, which I have shown in the schematic energy level diagram. And conduction band minimum, and with copper doped cadmium selenite, copper level, those are present, that is 0.2 electron volt lower in energy than the native level which are present in that systems. Then the electrical properties, for that purpose we have designed and fabricated a stainless steel sample holder, metallic sample holder in our laboratory and the metal workshop which is present in the department. So the beauty of this system is that you can do the electrical as well as the optical measurements simultaneously under the same conditions. All of us are knowing what the people are doing. They are doing electrical measurements in one sample holder and the optical measurements in another, or you can say in the air. Okay, and due to which what will happen, the experimental conditions are totally different in the two types of measurements, and then they are comparing with each other, which is not a correct way. The actual things is that all the conditions, environmental or experimental conditions, those should be same for different type of measurements. So for that purpose we have made, here we can go up to liquid nitrogen temperature, and if you want to go above the room temperature, we have kept a heater, okay, below the thin films, okay, or substrate you can say. And there are two windows, cross windows we have used for that purpose. From one end one can send the light and through a spectrophotometer, and from the other end one can measure the transmittance or absorbance spectra or so. And you can see in the left, you can see the sample holder design. And there we have, you can see we have kept a thin films on the glass substrate. Two electrodes are made, have been made for the electrical measurements. However, through the center, the light can pass from one end to other end. Okay, and at the other end, you have kept the spectrophotometer. We can measure the transmittance and all those things. Okay, a sensor is kept which can measure, which has been put on the film, so that directly you can measure the temperature. All these things have been done inside a vacuum chamber. And why vacuum is required? I have already told you, these are very low currents. So what will happen? The environmental effects or the electromagnetic radiations which are present in the environment, that will give the spurious current and all those things. And not only that, when you will go the below temperature, if the vacuum is not there, if the air is there, that will liquefy and you will get the moisture content and all those things. So for avoiding that thing, we have made a sample holder with a metal stainless steel here for that purpose. This conduction, basically three conduction mechanisms are there. One is in the extended state, that is basically taking place at a high temperature, and there one can use the relation sigma d, that is sigma minimum, that is their minimum metallic conductivity exponential minus EC minus EF upon KT. And we know EC minus EF is nothing, basically this is the activation energy. The second case is that the conduction in band tails, this is normally taking at low temperatures, and in that case the sigma d, that is the electrical conductivity, that is given by sigma 1 exponential minus E1 upon KT, and E1 is nothing, basically ED minus EF. Okay, and third case is the conduction in localized states. This is very low temperature, this thing is taking place, and in that case sigma d equal to sigma 2 exponential minus delta W1 upon KT, and W is the hopping energy and all those things. So from here one can calculate the activation energy by plotting ln sigma versus 1000 over T curves. Now we all of us are knowing that very low temperatures, what will happen? Hopping process is taking place. Okay, so in that case the conductivity decreases due to the gradual decrease in the temperature, and in that case sigma d varies exponentially with T to the power minus 1 by 4, and which indicates that charge transport is taking place is due to the variable range hopping in states which are very close to the Fermi level. And EF, so here you can write sigma dt to the power half equal to sigma naught exponential minus T naught upon T to the power 1 by 4. And from here one can calculate the density of hopping sites at the Fermi level, that is given by T naught, that is equal to C naught alpha Q upon Kn. These are the standard formulas which all of you have used whenever we are discussing the low temperature phenomena and all those things. The hopping distance R and the average hopping energy, those are given by these two relations, that is R equal to 9 upon this one, and W is equal to, which is known as hopping energy, that is 3 upon 4 pi R cube NEF. Okay, and NEF is basically, that is the density of hopping sites and all those things. So these things have been plotted here, and you can see here there are two different regions. One is at high temperature and the other one is at low temperature. So different hopping mechanisms are taking place here. Okay, and from the slopes of these curves one can calculate the activation energy, and you can see from here that at high temperature the activation energy is low as compared to the activation energy at the low temperature. Means you need more and more energy to take the electron, to move the electron in at the low temperature level or so. Different parameters are there which we have calculated using these theories and all those things, like density of states, the value of R, hopping energy, and all those things. And these have been tabulated in the table. So I will not go very detail in this one. Then the Hall measurements. Okay, and all of us are knowing that through the Hall measurements, we can find out that what type of charge carriers are present, because whenever we are going to fabricate a device, electronic device, in that case, we need that type of charge carrier. Suppose we are going to make PN junction or something, that is simplest device. So you must know a P type and N type, whether P type of material is there, whether N type of material is there. So we can see from here that cadmium selenide, which is undoped, that is having N type conductivity charge carriers. We have doped with 1%, in that case also it is N type. But when we increase the concentration of copper 5%, we have got the change in the charge carriers, type of charge carriers, and it will become P type. Hall measurements all of us have done in the 11th, 12th or graduation classes. Okay, so I will not go into the detail of that one. Okay, but when we are going to do these measurements in vacuum, so we are supposed, sorry, in thin films, we are supposed to take a lot of precautions and all those things. So that one. Then the mobility lifetime product. Okay, so these are the expressions which we have used for this purpose, and these are the general expressions which are available in the textbook. Okay, so concentration of photoexcited electrons, if we are interested, then that is G into N, and G is nothing, basically that is the free electron generation rate, that is rate per unit volume, and tau N is the lifetime. Okay, so then the effective light flux, that is defined by this relation F effective, that is F naught exponential minus alpha d. Alpha is the absorption coefficient, okay, and D is the sample thickness. And from here one can find out the mobility lifetime product, that is known as mu tau, by this relation which is here. Now L drift, that is known as mu tau into E here. So this has been done in the same sample holder which we have used here. Here we have used Keithley 6517 for the measurement of the electrical current, and power supply. For the power supply, we have used Keithley 224. Okay, and then we have used a light source through which is passed through a monochromator, and in the other side we have a spectrophotometer, and this is a general expected spectra, that is the incident photon plus a spectrum of light source which we are using in that case. Then what will happen, these are some of the data which we have obtained through this experiment, okay, for the mu and tau. So this we can see here, these we have plotted here, and from here different voltages have been used for this purpose. We have varied from 10 volt to 50 volts or so, and from there we have calculated the L drift using those relations, and at some particular voltage, that is 50 volt applied voltage, okay, we have calculated some of the things, and then we have tabulated on this much, and from this table we can see that the photosensitivity, which is a ratio of sigma photocurrent divided by dark current, D we are using for the dark current, so that increases more than 10 times, or 1 order changes there when we are doping with copper or so. And mu tau product, that also increases, okay, 2 orders changes there, and the L drift, that is the diffusion line, you can say that is also increases around 1 order changes there, that is from 3.4 to micrometer to 2 micrometer. So you can see why we are getting the larger mu tau product, and after the doping of copper, that is due to the increase in the lifetime of electron charge carriers which are present in the copper, and due to which what will happen, a decrease of the capture cross section of the electron is taking place. Now this thing has been verified by time of flight experiment also. This is because, you know, in experimental field we have certain advantages and certain disadvantages also. Advantages is that whatever is going on inside the material or whatever properties are there, those you are getting, okay, but at the same time whatever results you are getting, those are right or wrong, that you do not know. Okay, so for that purpose you are supposed to verify your results with other techniques also. Okay, so for that purpose we have again designed and fabricated an experiment, that is time of flight experiment, and I will show you that these results are in good agreement with the for that experiment. And for that time of flight experiment we are using the pulse laser 1064 nanometer wavelength is there, the pulse width is 10 nanosecond, okay, that we are using, and we have made a aluminum semi-transparent electrode on the film which has been deposited on the glass substrate. Okay, we are using for this a DC voltage source, and when we are giving a pulse of 10 nanosecond or so, normal oscilloscopes cannot be used for that purpose. So for that purpose we are using the Tektronix oscilloscope, through which we can record this data, because these are very fast process. Sometimes these are nanosecond processes are there, so one should be very careful for recording such type of data. So that thing we have done. Here we can see from this these spectra which we have taken using the time of flight experiment. Here we can find out the rise time and the transit time. Okay, there are four things are there: rise time, transit time, lifetime, and fall time. Okay, so those we have tabulated in the table, and from here we have calculated the mobility which we have obtained around same, that does not much change is taking place after the copper doping also, and from there we have obtained the mu tau product. So here we can see that the mu tau product, increase in the mu tau product is taking place after the copper doping. A small discrepancy we are getting in the time of flight experiment, so which is due to the wavelength of the laser light which we are using. One is we have used the laser which has low penetration depth, absorbed the surfaces of the thin films, okay, increase in the surface recombination, and increase in the recombination rate of photo generated electrons with holes. All of us are knowing that when we are giving a pulse of the light or some wavelength to a material, what will happen, the electron holes are generated, okay, and they will recombine if the surface defects are there in that case. So that is then the another experiment, that is the steady state photocarrier gating experiment. This is a very good experiment through which we can find out the diffusion length and all those things, because all of us are knowing whenever we are going to use these material for the optoelectronic purposes, device purposes, we must know all the parameters, and these are the parameters like carrier lifetime, diffusion length, and energy band gap, conductivity, photosensitivity, very important parameters. So for measuring the carrier diffusion length, we have designed and fabricated an experiment that is known as steady state photocarrier gating experiment, and which you can see the experimental setup is there. Here a helium neon laser we have used, which is a continuous time. Red wavelength we have used 600 nanometer or so. We have used a beam splitter for dividing this helium neon laser beam into two parts. One is going through the neutral density filter, then chopper is there for making the pulsating one, then one mirror is used, M1, and then a polarizer, and then this beam is reaching to the sample. However, the other part is going through the mirror M2, then two polarizers we have used P2 and P3, and they are reaching to the sample, and we should try they should fall at the same time. Then the angle which is making, that is very important for the calculation of these parameters. Okay, so these parameters which we have plotted and calculated, that is the voltage dependence of photoconductivity for thin films. Okay, and this here, the recombination, surface recombination effects we have seen here. Here in this case, the L diffusion, that should be very low as compared to the 1 over alpha, then only we can perform this experiment. Okay, applied voltage which we are using for this experiment, that should be ohmic in nature. Okay, and for that purpose, first of all, we are doing the IV. We have taken the IV characteristics, and there we have seen that these IV characteristics, that is ohmic, or you can say linear up to 100 volts or so, so there is no problem. Okay, so all these are the typical conditions for doing this experiment here. And here we have calculated the beta, and we have plotted beta with the electric field which we have applied here is. Okay, so here we can see that beta is independent of the applied voltage, which ensure that diffusion prevails over drift, and no variation of beta up to 1000 volt per centimeter we have observed in this case. Okay, and then we have tabulated these things in the table, and here we can see the L diffusion length, that is decreases when we are adding the copper on this material as compared to the undoped one. Okay, and decrease of EC minus EF with doping, that is due to the higher electron occupation of the recombination centers which are present in that materials, and less centers available for electron trapping. Means when high electron occupation is taking place in the recombination centers, so the number of defect centers are less, and in that case, for the trapping, okay, less centers will be available for the electrons, and more centers will be available for hole trapping. And increase of the electron mobility lifetime product, and a simultaneous decrease of the whole mobility lifetime product is taking place, which is here. Then the next experiment, that is the thermally stimulated current measurement, that is known as in CdSe measurements. Here we are keeping our sample at a very low temperature, and then we are shining a light, high intensity light, for certain few minutes or so, and then we will switch off. Then the electron hole pairs which are generated, those will be trapped in the defect centers, and then we will start heating from the low temperature to the room temperatures, and during that time the energy is required to the electrons which are trapped in these trapping centers, and that study, if we do, we can get very good information for that experiment. So here we are using light source. You can, the same experimental setup is used for that one. Voltage source is applied, temperature controller is there, and the things are monitored in the computer also. So different, there are two methods. One is different heating rate method, and the other one is Gaussian fit method. So these things we have used here, and these are the data. Okay, so here you can see the trapped energy, that is we are getting around 0.68 electron volts or so from these setup, these measurements, and this much. This is that earlier one is for the undoped one, and this is for the copper doped one. So these values we have kept in the table, and which has been calculated using the two methods. One is the Gaussian fit and the other one is different heating rate. Okay, so energy of the trap depth, you can say, in the undoped one we are getting 0.68 plus minus 0.01 electron volts or so, and we can see with the same these two methods we are getting the same value. However, with the copper doping there is a very also we are getting the same thing. The number of trapped states which we have calculated, we can see here that is increased when we are adding the copper inside this much. And then the capture cross section ST, which we have calculated, that increases 1 order change approximately is there. Okay, so this is in good agreement between the values of the trap depth calculated from these two methods, that is Gaussian fit as well as different heating rate method. So we can say the value of ET is very, very reliable in this case. So we can see here, we can say here that the trap energy levels in the copper doped cadmium selenide thin films are closer to the conduction band. The trapped electrons can easily escape to the conduction band because the trap energy levels are very close to the conduction band. Silo trap levels originate from doped impurities within the entire crystal, and the trap density that we have calculated, those are higher than the concentration of defects in crystalline cadmium selenide, which is due to the decrease of nanocrystalline grain size. All of us are knowing when the grain size will decrease, the number of defect centers, those will increase. Now these capture cross section of traps are low due to the strong repulsive barrier to capture carriers, and this capture cross section ST, which I have represented in the table, that decreases after doping, which shows an improvement of the transport properties of thin films is taking place. Then the last experiment which I will discuss, that is the constant photocurrent method. Here we are using a source, okay, where light source is there, and then the light is passed through a monochromator so that we can create the single wavelength. Then we are converting this into the pulsating ones. For that purpose we are using a chopper here. Then a beam splitter is there through which we can divide this beam okay into two parts, same beam, and then the one beam is passed through this beam splitter, and that is focused with the lens, and that is falling on the sample. However, the other beam that goes to the photodiode, and this photodiode is connected with a lock-in amplifier, and another lock-in amplifier is used is connected with the sample. Okay, so in this method basically the photocurrent is kept constant, and that's why we are saying this is a constant photocurrent method. By continually adjusting the light intensity I naught while the photon energy is scanned across the spectrum. For sub-band gap region, the value of alpha is given by alpha h nu equal to constant upon n ph h nu. Okay, by measuring intensity that keeps photocurrent constant at a predetermined value, we can find out the spectral dependence of alpha. Okay, and the constant in the above equation is obtained by matching CPM curve with the obtained by transmission measurement. So we need to do transmission measurements as well as constant photocurrent method, and from using this relation one can calculate the density of defect states which are present here. Okay, so here we have done basically we have taken the cadmium selenide, then this film is annealed, and then after that there are two films, basically three films we are taking. One is as deposited, the other one is annealed at higher temperature, and third one is the low light soaked. this much. So we can see here from this spectra alpha CPM which we have obtained that the increase in subband gap absorption after light soaking and annealing is taking place, due to which what will happen, an increase in defects which are probably due to the dangling bonds. All of us are knowing that during the preparation of thin films of such type of semiconducting materials, the large number of bonds are there which are broken, and these broken bonds are acting are known as dangling bonds, which may act as a recombination centers. So what will happen, the increase in the energy, that is which is known as tail state energy, EU, which is a measure of disorder in the material, that is due to the taking place due to the thermal induced structural disorder, higher absorption after surface treatment by light, which we are doing, higher density of states below mid gap after surface treatment, and higher electron capture cross sections or lower electron mobility you can see, and which you can see from the table also. Okay, different parameters have been tabulated in the table. So then I will not go, I will leave. I think the time is almost complete. I will not discuss the dopant effects because time is not there. So I will. So in short, what we can see, these nanocrystalline hexagonal structure of thin films, whether doped or undoped, they have been confirmed from the XRD analysis. Spherical shape of nanomaterials is observed from the transmission electron microscopy micrographs. Scanning electron microscopy investigation has been done, which illustrates the uniform distribution of these nanoparticles over the glass substrates without any cracks and holes. Atomic composition of thin films extracted from EDX measurements is in agreement with the desired composition used during preparation of materials. Blue shift in the band gap of nanocrystalline thin films as compared to bulk confirms the quantum confinement effect. Shift in the band gap values after doping is basically due to the formation of localized states and size quantization effect. PL spectra consists of band age emission peak as well as defect related peaks. After doping, PL spectra spans visible range, which is very useful for making the luminescent devices. Okay. Then from time of flight measurements, the dispersive type of transport mechanism is observed. Mobility lifetime product determines the performance of optoelectronic devices. And here we have obtained the reduced value of mu tau as compared to other measurements. It's basically due to the low penetration depth of laser light used, because in experimental field we have limitations also. The equipment, these are the costly equipment, so whatever is availability in the laboratory, that is used for that purpose. The quality of the material used in solar cell designing depends on the minority carrier diffusion length. SSPG, that is steady state photocarrier getting technique, is conducted to calculate the carrier diffusion length. Significant decrease in the carrier diffusion length with doping is observed due to the decrease of EC minus EF. Thermally stimulated current measurements provides an effective medium for the interpretation of transport properties of the devices. And with doping, the capture cross section, which I have represented at AST, decreases, resulting in improvement in the transport properties of cadmium selenide films. So this is all about, and thanks to all of you.
Thank you very much, sir. Thank you for this very informative and very nice lectures. So now the session is open for question. Audience, please. If you have any doubt, any question, you can ask. So there is one question in the chat box. So I will read this question. So question is, he is asking that you show in your results with the doping of copper percentage, the crystallite size increases. So kindly explain the reason behind this.
Can you repeat it again?
So with the doping of copper concentration,
yes,
the crystallite size increases.
Okay. Basically, what will happen if you are adding the copper inside that material? You know, the diameter of the copper is large. Okay, so what will happen due to that when it will go inside the material? Okay, uh, when it will go inside the material, the what will happen? It will make the bond, and there may be a possibility that increase in the size is taking place. Number one. Number two, the other reason may be there, that is we have prepared our film in the presence of some carrier gas. Yeah, I have already told you we are making this film using the physical vapor deposition technique. So in that case we are using a carrier gas which whose and carrier gas is inserted inside the chamber, vacuum chamber, by a very fine nozzle of the size of micron size also, and the direction of this nozzle is towards the direction of the particles which are uh, going towards the substrate. So due to which what will happen, these particles, they which are coming from the boat also, they will not get sufficient time to interact with each other. So during that process there may be a possibility that the particles which are reaching towards the substrate, they will reach directly to that much, and they will not have much time to interact with each other. Okay, so that is the another reason. Okay,
Yes, sir.
anyone else?
There is one another student who is asked, sir. There is one another question. High
Yes.
sensitivity, high resistivity substrates during the thin film. Why thin film deposition? Why it is required, sir?
Basically, for the optical measurements, there is no problem. You can do because you are not taking any contacts or so. Okay, the light is passes from one side to other side. But in the electrical measurements, I have already mentioned during my talk. In the electrical measurements, what will happen? The electrons will flow from the material, and if we are making the planar geometry, what will happen? The electron is passing from one end to another end, and these are the semiconducting materials, so they are behaving like a resistance. So it is simply a Ohm's law, that you are passing a current through a resistance and there is a drop in the current and all those things. But what will happen here? You can see you have deposited your film on a substrate, so there are two resistances are there. Okay, one resistance is of the film and one resistance of the substrate. So what will happen? This is a parallel combination of the two resistances. If you see, okay, all of you have read that parallel and series combinations are there. So in the parallel combination, what will happen? If the current will flow from that resistance which has the lower value, that is the easiest way. Electrons will follow that path. So if you will have a substrate whose resistance is low as compared to the film resistance, then the electron will flow through the lower resistance, means the electron will flow through the substrate, and whatever results you are getting, that will be the property of the substrate material. So that's why we are depositing these films on a very high resistive substrate, where the current or the electrons will pass through the film only, not through the high resistive materials. Okay, that is the actual reason. You can simply just assume there are two parallel resistances. So one is having a higher resistance and one is having a lower resistance. So the electrons or the current will pass only through the low resistance medium. Okay, so that is the actual thing. That's why we are using a substrate which has high resistivity. Okay, normal soda lime glass and all those things we are using everyday life, they are the alkali glasses, and alkali metals, they are providing some conductivity into those glass slides. So that's why we are using the alkali free glass slides. Next question.
Yes, sir. Next is physical thin film deposition methods are done in vacuum only. Then why did you divided them into the vacuum and sputtering?
In the sputtering system, basically we don't need the vacuum. One should understand, we do not require a very high vacuum. Okay, In the sputtering system, we are using a argon gas, okay, for making the plasma. However, in the cases of other techniques, we are removing the gases and we are not using any other gas. Okay, so that's why we have divided it into two parts. One is vacuum and other one is the sputtering. So sputtering, since the basic principle of the sputtering system is that a plasma is created of the inert gas, and that inert gas normally we are using the argon gas because it is easily available. Okay, we can use helium also, there is no problem. Okay, so when you between the two metal plates or electrodes, so when this argon gas will be there, argon ions will form and they will collide the target surface. Okay, so during that process, the atoms or molecules, they will come out from the target, and you have made the target material which you want to deposit. So yeah, that's why we have divided into two parts. Okay.
Thank you, sir. There are few questions, but we will share your email ID in the.
Yes.
If audience have any doubt or any query, they will contact you, sir.
Okay.
Thank you very much, sir. Thank you for the informative lecture, and thank you being with us in this session.
Okay.
Thank you, sir.
Okay, and once again, thanks to all of you
Thank you, sir.
for giving me this opportunity. Okay, so thank you.
Sir. Thank you.
Okay.
So next speaker we have Professor G.S. Sahane. Sahane sir, good morning.
Very good morning, Dr. Ashok ji.
Sir, please unmute yourself.
Am I audible?
Yes, sir. Yes, sir.
So, very good morning, Dr. Ashok ji.
Sir, please increase the volume. Your volume is too low.
Oh.
Yes, sir. Now it's okay.
Now audible?
Yes, sir. Now it's audible, sir.
Okay, sir.
Okay. So good morning, sir, and thank you very much for accepting our invitation for delivering this lecture on basics of nanomaterials in this 1 week faculty training program. So you are welcome, sir, in this course.
Thank you.
So now I will introduce our next speaker, Professor G.S. Sahane. We have with us Professor G.S. Sahane, Professor and Head Department of Electronics, DBF Dayanand College of Arts and Science, Solapur, Maharashtra, as a speaker of this second session of day 2. It's my pleasure to introduce Professor G.S. Sahane to the audience. He will deliver his talk on basics of nanomaterials. So Professor Sahane is having a teaching experience of 35 years. His research interest includes gas sensors, instrumentation, magnetic materials, and ferrofluid. He has supervised research scholar for PhD in physics and electronics also. He has published more than 55 research articles in SCI journals with over more than 900 citations. He has successfully completed 3 research projects funded by UGC and 1 major research project funded by SCRB DST New Delhi. Professor Sahane has visited Poland in 2000, Russia in 2001, France, Switzerland in 2019 for international conferences and collaborative work. He has published 16 books. Dr. Sahane has also worked as Indian Academy of Science INSA NASI Summer Research Fellow at National Physical Laboratory, New Delhi in 2009. He has delivered invited talk in various national and international conferences. He has received various awards of distinction. The first one is Dr. H.N. Jagtap Best Teacher Award by Dayanand Institution in 2011. Best Teacher Award by Solapur University, Solapur in 2017, and many more. He is also the executive editor of DAV International Journal of Science, and he is a reviewer of international journals like Journal of Alloy and Compounds, Material Research Bulletin, Material Science in Semiconductor Processing, Material Science and Applications, and sir is also member of various national and international bodies. So thank you, sir, for accepting our invitation for delivering your talk in this FTP. So now I request you to, sir, please start your lecture. Thank you, sir.
Thank you, Dr. Ashok ji, for nice introduction. Just I will share my screen.
सर यस सर सर एक बार वो माइक का आप थोड़ा ठीक कर लीजिए, अदरवाइज फिर वो वॉल्यूम इसका.
Now is it audible?
Yes sir, now it's audible sir.
Yes, I have to hold it like this. Is screen visible?
Yes sir, screen is visible sir. Okay sir, please start.
So very good morning to all of you. At the outset, I would like to thank the organizers, in particular Dr. Ashok Kumar, for giving me an opportunity to interact with you. Friends, looking to the diverse audience from different subjects, physics, chemistry, and even engineering. So I have decided to discuss in general about the nanomaterials, their applications, and then in particular about the work that we have done in our laboratory. So what is nanomaterials? Just one. Nanomaterials are the structural components with dimensions less than 100 nm. So for physics, it may be a sort of repetition, but for engineering or others, we will have some discussion about that also. So we know that 1 nanometer, 10 to the power minus 9. Now, what is the speciality? Why this limit, 100 nanometer? Now, if the size of that material is above 100 nanometers, its properties are almost similar to that of bulk. No change, effect of size, no effect of size. But if we reduce the size of that material below 100 nanometer approximately, or generally we can call it as critical size, below that, the properties of the material changes. It shows different properties from the bulk. And therefore, this branch is important, particularly to the, with respect to the aspect of size. If we reduce the size, if we take it into the nano scale, it shows different properties. So what is nanotechnology? It is the creation and use of materials or devices at the nanoscale. So it is just a primary idea. Look at this. Just this window is disturbing. Now look at this, a three-dimensional structure first, 3D material, whose dimensions are greater than 100 nanometers. We call it as bulk material, because its properties are similar to that of bulk. But if we reduce one of the dimension of that material less than 100 nanometer, say it becomes like this, it becomes a two-dimensional sheet. We call it as a nano sheet, a two-dimensional structure. If we reduce one more dimension of that below 100 nanometer, then you will get a structure like a nanorod or a nanotube. It is a one-dimensional material. And if we reduce all the three dimensions below 100 nanometer, we get a zero-dimensional material called a nanoparticle. So important thing is that at least one of the dimension must be less than 100 nanometer. Then and then only it will show the effect of size. Note that the idea of nanotechnology was first introduced by Richard Feynman, a great scientist, in 1959. In his lecture, "There is a plenty of room at the bottom." See, about 62 years back, when the technology was not developed, at that time he predicted advanced microscopes, developments in the fabrication methods, possibility of atom-to-atom assembly. So in a real sense, he is a great visionary. Now, question is, are nanomaterials new? Answer is no. Many existing technologies already depending on the nanoscale materials and processes. Say, for example, let us take the examples of Ayurveda. So in Ayurveda, there are different bulbs. They used to grind the material to a fine powder. So knowingly or unknowingly, they were using nanomaterials to get that particular effect of medicine. They have to grind, they have to reduce the size of that particle. They have to make a very fine bhasma. Another example, glass windows in the cathedrals. Look at these beautiful colored glass windows. They are prepared nearly 2000 years ago. Very colorful. They have used gold nanoparticles, silver nanoparticles for these colorful windows. Similarly, another very famous example of this Lycurgus cup. What is the beauty of this? Look at this. When this cup is illuminated from outside, it appears greenish. And when it is illuminated from inside, if the source of light is within that, it appears to be red. So this effect, it is the effect of surface plasmons, and it is due to the nano materials of gold and silver embedded in that material. So knowingly or unknowingly, they are using this technique. Another example, the Damascus sword, a very famous sword of that time. Very fine blade, flexible blade with sharp edge. And that sword was made in the nearest countries from the steel imported from southern part of India, particularly Tamil Nadu, Kerala. And when it is analyzed in the modern days, it was analyzed again, and it is found that carbon nanotubes were there in that steel. So which increases the quality of that sword. So question is, what is the effect of size? Totally different properties from those of the same material in the bulk form. So as the size changes, it changes the properties of that material. Properties such as chemical reactivity, optical gap, mechanical strength, electrical conductivity, magnetic properties, and so on. So all these properties can be tuned, can be changed just by changing the size of that nanoparticle. Previously, what we have to do, if we have to change the optical gap, what we have to do? We have to add some impurities. We have to dope. We have to make a composite of different materials. But here, just by changing the size of the material, we can change its optical properties. We can change its electrical conductivity. We can change its magnetic behavior. So that size has a prominent role. Look at some examples. Say chemical reactivity. So note that chemical reactivity depends upon the number of chemically active atoms on the surface. And if we plot the graph, percentage of the bulk atoms and percentage of the surface atom as a function of particle size, you will see that as size of the particle reduces, percentage of the bulk atoms decreases, whereas percentage of the surface atoms increases. So as the number of surface atoms, percentage of surface atoms increases, its chemical activity also increases. Melting point. As we reduce the size of that nanoparticles, you will see that melting point also decreases. Gold at normal gold, it is in the solid form, but this is a gold colloid solution made up of gold nanoparticles of the dimension less than 5 nanometers. So here we will see that melting point of the material also changes with the size. Optical properties. Generally, we measure the optical band gap of the bulk material. What we mention is the optical gap, band gap of the bulk material. Now, if we consider a single atom, there is a valence energy level and conduction energy level, and that gap we call as band gap. But if we increase the number of atoms, say 1 or 2 instead of 2, now there are that energy level splits, and see the effect on the band gap. As the number of atoms increases, a single energy level is changed to a band, and its effect is the band gap also decreases. In the reverse way, if we decrease the size of the material, band gap of that material also increases. Very interesting property, very useful in quantum dots. So look at these. These are the nanoparticles of semiconductors, cadmium selenide nanoparticles, having different size and illuminated with the same light. You will see different colors. They are emitting different colors. So this is the change in the optical gap due to the size. Mechanical properties are also affected by the size. Hard and brittle materials becomes ductile. Strength of materials can be increased. So it is very useful in preparing the materials. A lightweight material, but having high strengths, useful for aircrafts, rockets, etc. Tougher and harder cutting tools can be made by using nanomaterials. Carbon nanotubes, very popular material, very interesting material. What is the beauty of this material? The strongest and most flexible molecular material. 100 times strength and density is 1/6 of that steel. If you compare this carbon nanotube with the steel material, its strength is very high, but still its density is very low. At the same time, its thermal conductivity as well as electrical conductivity, they are very high. High conductivity, high electrical conductivity makes them suitable in number of applications. Magnetic properties. If we take a bulk material, or if the size of that material is greater than 100 nanometers, multi-domain particles, it shows hysteresis with retentivity, some retentivity and coercivity. Hysteresis look well known. But if we reduce the size of that particle, magnetic particle, when that size becomes less than critical size, then thermal energy is sufficient to overcome that anisotropic energy, and it will easily change its direction due to the thermal energy. So material shows super paramagnetic nature, no retentivity, no coercivity. So a ferromagnetic material becomes a super paramagnetic material. So important point about this nanomaterial. Below a critical size, material properties are size and shape dependent. Very, very important. So just by changing the size or just by changing the shape of that material, we can change the properties as per our requirement. So this is the most important concept in nanotechnology. Now, this is again an introductory part for PG students. No, it's not new. So for synthesis of nanomaterials, there are two approaches: top-down approach and bottom-up approach. What is meant by top-down approach? Look at this simple figure. I have shown a special image of the Ellora caves from Maharashtra. What is the beauty of this? So this is carved from this temple. It is the Kailas temple, carved in a single stone. That entire hill was carved to form a two-storied Kailas temple. Very beautiful structure, carved from a single stone. So this is the top-down approach. So unwanted part is removed so as to get the desired structure. In the second approach, bottom-up approach, we have taken the example of this Qutub Minar. So here, this is a huge structure, but built from small units, small pieces of stones arranged in a regular fashion. Bottom-up approach. It can be seen from this structure. So let us suppose that this is our desired nanostructure. It can be obtained either by a top-down approach or bottom-up approach. In top-down approach, we have to remove unwanted part so as to get the desired structure. In bottom-up approach, we have to arrange these atoms in such a fashion so as to get the desired nanostructure. So depending on this, there are different methods. Say, for example, in the top-down approach, there are different methods are ball milling, lithographic techniques, say X-ray lithography, electron beam lithography, deep pen lithography, etc. On the other hand, in bottom-up approach, there are different physical vapor deposition methods, chemical deposition methods, sputtering methods, chemical co-precipitation, sol-gel, hydrothermal, sonochemical, and many more. So basic approach is different. Now, when we form a nanomaterial, we have to characterize it. Now, which characterization? What kind of characterization is needed? So it depends upon which type of characterization is to be done, depends upon the properties of interest. But very important, size, shape, and structure, and sample purity, they are very essential. Why? Because they are the factors which decides the property of that material. So sample purity will decide whether the composition is correct or not, and properties are decided by its size, shape, and structure. And for that, we have to use these famous techniques, not new: X-ray diffraction, scanning electron microscopy, transmission electron microscopy, atomic force microscopy for the structural analysis, and energy dispersive X-ray spectroscopy for compositional analysis. So let us discuss in brief X-ray diffraction technique based on Bragg's law, very well known for the students particularly. So X-rays, in this case, you will get a X-ray pattern like this from the Bragg's diffraction. And this X-ray pattern is typical for a given material. It is the fingerprint of that material. So when we synthesize any material, whether the given phase is formed or not can be identified by taking the X-ray diffraction pattern of that sample. So we have to record that X-ray pattern, and from these peaks, positions of the peaks, we can confirm whether the synthesized material is same or not. Each peak can be assigned to different planes. So this is again a unique property of that material, and therefore it is very essential to take the X-ray patterns of the synthesized material. Again, the surface morphology of that material can be obtained with the help of this scanning electron microscopy. An electron beam is used to obtain the image. So you will get high resolution. So you will get images in micrometer range. On the other hand, another microscope, transmission electron microscope, TEM. It is based on the transmitted electrons, but you will get very high resolution. So you can observe these nanoparticles. You will get resolution in nanometers. So for the materials in the powder form, you can get its TEM so as to get the details. But if your material is in the form of film, we have to use atomic force microscopy to get its surface features. So it is again based on a very simple principle. A laser beam falls on that tip moves on that surface, and as this tip moves up and down, the laser beam reflected intensity changes, which is detected by this photodetector and so on. So this technique is useful to get the surface information, surface roughness and other parameters of that surface of the film. So depending upon the method used, depending upon the synthesis parameters, you will get different nanostructures. So nanomaterial, it is a zero-dimensional, but if it is a one-dimensional or two-dimensional, we call it as nanostructure. So you may have a spherical particles, triangulars, cuboids, pentagonal. You can have belts, nanorods, nanoflowers, and many more. So these are the different, of course, these are the not only, but there are a number of structures. And remember that the properties of that material is strongly affected by the structure, shape also. So these nanomaterials have applications in variety of fields. Wherever there is a material, wherever we require a material, we can use this nanotechnology to enhance the quality of existing materials. For example, it can be used in civil engineering, mechanical engineering, electronics, medicine and health, defense, aerospace, energy and environment, agriculture and food, textile, cosmetics, paints, metallurgy and materials, many more. Wherever we have to use material, we can use nanomaterials to enhance the quality of that material. So let us discuss in brief about different applications. Say in civil engineering, so by addition of nanomaterials into the cement concrete, it can improve the strength of that cement. Generally, they use nano silicon dioxide, ZnO2, Al2O3. So these nanomaterials are added to that concrete, which enhances the strength of that concrete. Application in steel also. Steel is one of the major component of the construction, and it is possible to develop new low carbon and high performance steel by adding copper nanoparticles. So it increases the strength of the cables, nuts, bolts, frames, etc. So it can be useful for the construction of bridges. Coating is another application. So self-cleaning glasses. So when that glass is coated with TiO2 nanoparticles, look at this lower figure. So it has the ability of self-cleaning. So this is also useful. At the same time, for the huge structures, nanosensors can be used. The nanosensors can be embedded in the structures to monitor the strength of these structures. Mechanical engineering. Nanocomposites formed by combining 2 or more nanomaterials to achieve better properties. You will get high performance, lightweight materials. Tougher and harder cutting tools can be made out of this. So it is also useful in automobile industries, that nanomaterials can be used to improve the performance of batteries, fuel cells, to increase the life of tires, paints, mirror, windows, even chassis, metallic bodies. All that we can use nanotechnology to enhance the performance of the existing materials. Even nanofluids can be used to enhance the heat transfer. Silver nanoparticles are a nanofluid with silver nanoparticles can be used as a heat conductor to remove the heat. So it is again one of the important application of nanofluid. MEMS and MEMS nanotechnology can be used to fabricate the structures at the micro and nano levels. Machines, switches, actuators can be fabricated at the nanoscale using these nanotechnologies. In electronics, again, it is, look at the first transistor, very small, very large size, discrete transistor. This is our integrated circuit, first integrated circuit. But as time goes, we have a better ICs in which large number of components can be fabricated in a single piece. And the number of components per chip is gone continuously increasing. In 1965, Gordon Moore predicted that the size of the transistor is continuously decreasing in such a fashion that the density of transistor will double after every 18 to 24 months. And it was an empirical prediction by Moore, and it was true also in the initial stages. But nowadays, that graph is deviated. It is rather difficult to reduce the size of these electronic components. Why? There are some problems in reducing the size of the electronic components. So as we go on reducing the size of the electronic component, there is a possibility of dielectric breakdown. As the distance becomes very close, possibility of dielectric breakdown. Similarly, another effect is heat dissipation. When current flows through these devices, heat is dissipated. And since the density of components is very high, large amount of heat is dissipated, which may increase the temperature and it may stop the functioning of that IC. So that is again a major problem. Again, also non-uniformity of the dopant atoms and quantum mechanical tunneling effects. So while fabricating the, while increasing the number of components, we have to use some another approach to increase the component density. So they must be operating at very low voltages, operating at very low currents. And for that, so I will mention some of the examples. Say CNT transistor, carbon nanotube transistor. Another, there is a news, junctionless nanowire transistor. No junction, but a nanowire can be used as a transistor. Single electron transfer devices, single electron transistor. So here the current flowing through that, which is in the few electrons only, and that is controlled by that gate terminal. So magnitude of the current is reduced, so it will automatically reduce the power consumption, power dissipation. Another devices, say tunneling diodes, resonant tunneling diode, it is possible because of that small barrier, tunneling barrier, a flash memory in which there is a gate, and we can trap the charges in that floating gate because of that thin barrier only. Flexible electronics, by using conducting polymers or by using silver nanoparticle paint, which can be used as a connecting wire, you can have flexible electronic components also. One more invention recently we have seen, silicon nanophotonics. So in these integrated circuits, for carrying a current, we have to use some conducting materials. Instead of that, a light is used as a information carrier. So in this case, along with that electronic components, that optical fiber, rather that optical fiber is also embedded, fabricated in the same chip, so that instead of transmitting the data in the form of electrical signal, it is transmitted in the form of light signals, which are very fast. So this will be very useful in increasing the speed of that device. Also useful in textile industry, stain-proof, waterproof, wrinkle-free textiles. So some nanomaterials are coated, zinc oxide, TiO2 nanoparticles are coated with these textile fibers, out of which you will get such wrinkle-free and stain-proof textiles. In cosmetics also, we can use nanoparticles for UV protections as well as for smooth skin. So almost number of applications are there. Biomedical applications. In the field of medicine, also we can use this nanotechnology. Say magnetic drug targeting, targeted drug delivery, we can call it. So what is our conventional method of taking a drug? We have to swallow that tablet or we have to inject that medicine in our body. So that medicine is circulated throughout the body. Even though it is required for a specific part of the body, it is circulated throughout the body. So required dose is very large. But on the other hand, if that drug molecules are attached to the magnetic nanoparticles, and by using that external magnetic field, we can localize that drug at the specific site. So this will reduce the amount of drug required for that particular direction. Also can be used for as a contrast agent for MRI, magnetic resonance imaging. We have to take the images of our different parts of our body, MRI. So in that case, these magnetic nanoparticles can be used to enhance the contrast of that man. Similarly, magnetic nanoparticles can also be used for magnetic separation of cells. We have to attach these magnetic nanoparticles to the desired cells, and then by using external magnetic field, we can separate these desired cells. Bacteria detection, a small circuit electronic component is also attached along with that necessary sensors on the teeth. Glucose sensors can be patched on our body, which can sense the glucose level and which can monitor the glucose. Another is hyperthermia. What is hyperthermia? Hyperthermia means to increase the temperature of that body. So these are some of the applications. Let us have more details about this magnetic fluid hyperthermia. So what is hyperthermia? Hyperthermia is a non-invasive method of increasing the temperature of tumor. So we know that cancer, a very dangerous disease, and there are a number of cancer patients. There are different methods of cancer treatment. Chemotherapy, radiation therapy is there. Surgery is there. So one more is there, and that is the hyperthermia, to kill the cancer cells by increasing the temperature of that. So it is found that these cancer cells can be killed if we increase the temperature of that cell up to say 42 to 46 degrees. At this temperature, cancer cell gets destroyed. But normal cells, they are not much affected at this temperature. So if that particular part of the body, if we increase the temperature up to say 42 degrees Celsius, 42 to 46 degrees Celsius, then cancer cells are destroyed and normal cells are not much affected. So destroying the cancer by this method, we call it as hyperthermia. And for increasing the temperature, a magnetic fluid can be used. So if we use magnetic fluid for that, we call it as magnetic fluid hyperthermia. So in this case, we have to apply a alternating magnetic field. So because of that magnetic field, these magnetic nanoparticles dissipate energy by the relaxation process. Let us see what exactly happens. This is the schematic diagram. So these are the cancer cells and magnetic nanoparticles are injected here. And it is then subjected to AC magnetic field. So when we apply AC magnetic field, then energy is absorbed by these magnetic nanoparticles during that relaxation process, and it kills the cancer cells. Let us see exactly what happens. Now we know that for these magnetic materials, there is magnetic anisotropy. Magnetization, these particles are generally arranged along gets magnetized along their easy direction. So when we apply a magnetic field to the nanoparticle, it gets aligned along the direction of that magnetic field. Say, for example, now the field is in the upward direction. This particle is also magnetized in the upward direction. Now, if we reverse the direction of that field, now there are two possibilities. Two processes may happen. One is nil relaxation and second is Brownian relaxation. In nil relaxation, the particle remains as it is, but its spin, its direction reverses without the rotation of that particle. So that spin, that magnetic direction, it's reversed without the rotation of the particle. On the other hand, in Brownian relaxation, that particle itself rotates. Here, the particle itself rotates. Our interest is in nil relaxation. In nil relaxation, as already mentioned, it is magnetized along easy axis. Say, for example, this is easy axis. And if we try to change its direction of magnetization along with that field, due to magnetic anisotropy, generally it is the hard axis. So we require some energy to change the direction. So that nanoparticle takes the energy from the magnetic field, and after passing that hard axis, automatically it gets relaxed it moves to the easy axis again. Look at this second diagram so that point will be more clear. So this is the alignment. The magnetic particle align in this direction. And if we reverse the direction, if you have to rotate that direction, if you have to change the direction of that field, it has to overcome this barrier. So to overcome this barrier, it takes the energy from that field, and from moving this part to this part, now that particle gives the energy. It dissipates the energy in the form of heat. So in this relaxation process, in this changing the direction of that material, energy is released in the form of heat, and this can be used to kill the cancer. Now, this heat generated by magnetic nanoparticles is measured in terms of a parameter called as specific absorption rate, SAR, which is given by this formula. It depends upon the concentration. It depends upon, specific heat, concentration, and slope of that graph from which you have to calculate that. Now, if we have to use magnetic materials for this application, there are two important requirements. High absorption rate. It must have high specific absorption rate. Its SAR must be very high, and at the same time, it must be biocompatible. What will happen if the SAR is low? If the SAR is low, you will require more amount of magnetic nanoparticles. You require more concentration, more dose of that magnetic nanoparticles to achieve the desired temperature. And therefore, with minimum dose of that nanoparticle, if we have to increase the temperature, then its specific absorption rate must be very high. And second parameter, biocompatible. We are injecting these nanoparticles in our body, living tissue. So it should not be toxic. It should not affect our body. And therefore, it must be biocompatible. So in our lab, we have synthesized Fe-Mn ferrite nanoparticles, a composite of Fe and Mn ferrite nanoparticles for magnetic fluid hyperthermia. Why this composite? Note that for biomedical application or for this hyperthermia application, most of the work is on Fe3O4 only. It is very famous candidate for biomedical applications. Because it has highest specific absorption rate, at the same time it is biocompatible. Another material, MnFe2O4, is also found biocompatible and having high absorption rate. So we have decided to make a composite out of that and to test its suitability for the magnetic fluid hyperthermia. For the synthesis of this composite, we have used a chemical co-precipitation method. Simple chemical method is used for the synthesis of ferrites. A well-known method, very simple. It is used in number of laboratories. What is the beauty of this method? This chemical co-precipitation method is very simple, inexpensive. It is a low temperature synthesis, does not require very high temperature, and at the same time, very important, good control over the particle properties. Size of the particles can be tuned, can be controlled by optimizing the reaction parameters such as temperature of the bath, pH of the solution, and ionic concentrations. So very simple method for the synthesis of nanoparticles. It is the chemical co-precipitation methods. So these are the XRD patterns of the synthesized material, different composition. You will see that these different patterns, I will not go in much details of the analysis part, but what information you will get from these X-ray diffraction patterns? First thing, by comparing the peak position, we can confirm whether the synthesized material is that ferrite or not, synthesized Fe-Mn ferrite or not. So we can confirm the phase. We can obtain its lattice parameters by using the simple formula A is equal to D square root of S square plus K square plus L square. So lattice parameters of that crystallite nanomaterial can be obtained. Crystallite size and strain can be obtained by using Williamson-Hall method, by plotting the graph between this simple equation beta cos theta and 4 sin theta. You will get the crystallite size as well as induced strain in that nanomaterial. So this X-ray diffraction patterns will provide lot of structural information, the crystallite size, strain, the lattice parameters. At the same time, that data can also be used to obtain the cation distribution. So this is our spinel structure, and there are two sites, A site and B site, tetrahedral site and octahedral site. and the properties of material are decided by the cations at tetrahedral and octahedral sites. So we can determine the cation distribution using these X-ray patterns. I will not go in much details, but that information can be obtained from that. Also, this figure shows the schematic of interionic distances and bond angles in the spinel structure, and by using different formulae, we can obtain the interionic distances as well as bond angles, which will be useful. This structural information is useful to correlate their properties, say for example, magnetic properties with the composition, with the structural changes. And for that, we require this structural information. Similarly, microscopic studies, TEM, SID, and HRTM images of some of the compositions. So you will get, say, look at this HRTM image, you will get nanoparticles having the dimensions few nanometers. So this structural information, its particle size distribution can also be obtained by using this TEM, SID, and HRTM images. Similarly, compositional analysis can be done with the help of, so you will get different peaks, and the percentage area of that peak depends upon the percentage of the respective components. You will get the number of composition of the film in percentage, wet percentage or atomic percentage. Now our interest, for our hyperthermia, it must have high specific absorption rate, and which depends upon its magnetization. So for that, magnetization measurements were carried out by using a vibrating sample magnetometer, and these are the different curves, PSM curves of that curve. You will see that the saturation magnetization changes with composition parameter. It increases, it reaches maximum for about x equal to 0.7. So when Mn concentration is about 0.7 in that composite, you have a maximum value of magnetization. Now, if we have to use these nanoparticles for biomedical applications, then we have to prepare a ferrofluid. What is ferrofluid? These magnetic nanoparticles are suspended in a suitable carrier. But in order to get a stable ferrofluid, these particles must be coated with some suitable surfactant, a capping agent. So in our case, we have used citric acid as a surfacting agent. So particles are capped with citric acid, and they are suspended in the distilled water. Distilled water is used as a carrier water. So this is a stable ferrofluid, but if we place a strong magnet here, all these particles gets extracted. If we remove that, again it becomes a dispersed medium of that. This is the experimental setup for the measurement of SAR, a schematic diagram and the actual experimental setup. So this is the sample holder, which is placed in a coil to which we are going to apply AC current. So this is AC high AC current generator. When that current flows through that coil, magnetic field is produced, strong magnetic field is produced, and this sample is placed. Its temperature is sensed with the help of temperature sensor and DAC system, which is attached to a computer. And there is a provision to adjust the frequency as well as the field of magnetic field strength. So these are the different heating curves. Variation of temperature as a function of time for different curves. You'll see that as time goes, temperature of that ferrofluid, temperature of that compound increases, and at the same time, if we consider the effect of magnetic field strength, as field strength increases, temperature also increases rapidly. The SAR is obtained from the slope of that initial part, slope of that curve in the initial part. And you will see that SAR, specific absorption rate, also increases. It has highest value for x equal to 0.7. Of course, it is because of the high saturation magnetization of that material. At the same time, you have to study its biocompatibility. So biocompatibility study was also studied by using stain L929 cell lines. These magnetic nanoparticles are injected in these cell lines and tested for 24 hours. You will see that not much effect is observed even after 24 hours. So it is this is the bar diagram for various concentrations. Cell viability as a function of concentration. You will see that for lower concentrations, there is cell death is very, very low. Cell viability, percentage viability is about 95% for this low concentration range. So for low concentrations, these nanoparticles can be used for hyperthermia applications. So in our laboratory, we have used this FEMN series. At the same time, after this, the work is in progress for doping some another impurity to enhance the SAR further. So this is all about the application of these magnetic nanoparticles for biomedical application. In our laboratory, we have also synthesized temperature sensitive ferrofluid for enhancement of heat. Now, number of times the conventional method of removal of heat from the hot object, these methods are either inadequate or they are not suitable. Say, for example, if the mechanical parts are moving or under reduced gravity conditions or in named MEMS, conventional methods of removal of heat or use of heat sink is not suitable. In these situations, we can remove that heat, we can increase the heat transfer by using ferrofluids. So enhancement of heat transfer by using, so it is based on the principle of thermomagnetic convection. So look at this simple schematic diagram. A rectangular loop is taken here, which is placed in a horizontal plane. Here is a small heater and small electromagnet is there. Now, without magnetic field, when the heater is on, the ferrofluid, this is filled with ferrofluid. Its temperature, because of that temperature, ferrofluid gets heated. And we are using a temperature sensitive ferrofluid. What is the speciality of that temperature sensitive ferrofluid? When the temperature of that ferrofluid is low, it shows magnetic properties. It can be moved by using magnetic field. But if the temperature is increased, it loses its magnetization and magnetic field has no effect. Very simple approach. When it is at low temperature, it is showing magnetic properties and can be moved by using a magnetic field. But when its temperature is increased, it loses its magnetization and magnetic field has no effect. So what happens in this case? To avoid our natural convection, removal of heat by natural convection, we have placed this loop in a horizontal plane. So natural convection is minimum. Now this is a hot object. Now because of its temperature, this ferrofluid gets heated. And when this ferrofluid gets heated, it loses its magnetization. When it loses its magnetization, now this region near this magnet, it attracts the ferrofluid from this side, which is cold. So this hot ferrofluid is replaced by this cold one. So this cold ferrofluid will again take the heat. It will go move in this direction. Here we have to use again a heat exchanger, which can remove that heat. A heat exchanger is here. I have not shown in this figure, but here is the heat exchanger. We can remove that heat here. So without using any external agency, external energy source, we can circulate that fluid, which can remove the heat. We call it as thermomagnetic convection. Now for this, we require a temperature sensitive ferrofluid, but what are the main requirements for that? For that, there are three basic requirements. It must have high saturation magnetization. Its Curie temperature must be very low, and it must have high pyromagnetic coefficient. It must suddenly change. So we have used MnZn ferrofluid and MnZn dy ferrofluid For this application, MnZn, a well-known temperature sensitive fluid, and in addition to enhance the properties, we have used rare earth dy for that. So I will not go in much details again. These are the XRD patterns of the MnZn for different composition as well as dy doped. For dy doped, for low doping concentrations, you will get phase wave, but for higher concentrations, a separate phase of dy FeO3 is also observed, shows that there is a limitation on the solubility of this dy in this host structure. Again, a similar compositional analysis, the structural information, magnetization measurements of the same, and this is the experimental setup in our laboratory for the measurement of Curie temperature. You'll see that with composition, Curie temperature is reduced. This is for MnZn series and this is for dy series. This is the synthesized field without time with magnetic field, and this is the experimental setup developed in our laboratory. Here is the heater, a magnetic field source, a temperature sensor is also there to measure the temperature of that fluid, and here is the heat exchanger to remove that heat also. So in this case, we can measure the temperature of that fluid without magnetic field and with magnetic field. You will see that this red one is without magnetic field and this blue one is with magnetic field. You'll see that this curve shifts in the downward direction. So maximum temperature is shown here. So without magnetic field, temperature of that hot object is high for these different compositions, but for with magnetic field, you'll see that temperature of that hot object is reduced and it has shown dy content concentration of 0.1 shows better performance. So we can use this also to enhance the thermal conduction. We have also studied in our laboratory gas sensor applications, synthesis of nanocrystalline materials, metal oxides, SnO2 as well as zinc oxide for the gas as a gas sensor applications, its structural analysis, surface morphology, AFM. This is the experimental setup, gas setup developed in our laboratory. Electronic system, microcontroller based system is also developed as a data acquisition system. This is the gas chamber where we can insert the gas, test gas, probes are there inside, and it is connected through this system to the computer, a laptop. And you will see that the SnO2L samples have shows better response for carbon monoxide gas also. So another application, looking to the diverse faculty members from diverse field. I have not gone in much details analysis of the cells, but just I have given a brief introduction about the work that we are carrying out in our laboratories. So I am very much thankful for the University Grant Commissions for sanctioning different projects, Science and Engineering Research Board for one more project, Indian Academy of Sciences for the fellowship, under which I have worked under Professor Kishan Lal, the then director of NPL. I have also worked in the laboratory of Dr. Pant. So I am very much thankful to Professor Kishan Lal, Professor Pant. These are the team members in our research laboratory, Dr. Jipre, Kore, Dhumar, Vidap, and Bangar. These are the active members of our group. Thank you very much.
Thank you very much, sir, for such a very nice lecture on magnetic materials. You have touched the basics of nanomaterials, their synthesis methods, properties in a very nice manner. So now the session is open for questions, queries. Participants, please, if you have any doubt, any question, please ask. Sir, I have one question.
Okay.
Sir, regarding this hyperthermia treatment,
Yeah.
which ferrofluid is much better?
Actually, in general, Fe3O4 is widely used, but
Yes,
we have also tried for the composite FeMn ferrite, and we have observed that for X equal to 0.7, the performance is improved. So that composition can also be used for this hyperthermia application.
Okay, sir. So there is another question from the audience. Is a hot ferrofluid automatically changes to cold ferrofluid?
Sorry?
Is hot ferrofluid automatically changes to cold ferrofluid?
Yeah. There is a heat exchanger. There is a cooling system on the other side. And when it gets cooled, naturally it attains its natural property of magnetization again.
Okay, sir. There is another question. As said by Professor Tripathi, nowadays nanomaterials are considered if they are falling below 40 nanometer kind of. What you say about this? They are asking about the previous speaker. Previous speaker told that nanomaterials are considered if they are falling below 40 nanometer kind of things. What do you say about this?
100 is a rough figure. Actually, the critical size depends upon which property and which material you are using. It is not fixed. Say, for example, magnetic optical properties change in the optical gap is well below 10 to 20 nanometers. Melting point, for that you have to reduce the size below 5 nanometers. Magnetic super paramagnetic nature, even for super paramagnetism, 40 nanometers. So it depends upon two aspects: which property you are going to study, and second, which material. So it is material dependent, it is property dependent. So 100 is a rough figure, not fixed, and it is not necessary that if we take 90 nanometer, it will show nano properties. No, depends upon that material and depends upon that which property you are interested.
Yes, sir. Thank you very much, sir. Next question we have. Please specify which method is suitable and accessible to check biocompatibility of the nanomaterials.
Actually, biocompatibility study we have not performed in our laboratory. It is available in Pune. There is one private laboratory which gives this information. We have to give the samples to them and they will do the analysis of that. These biocompatibility tests are not available with us. We have to take the help from others outside.
Okay, sir. Okay, sir. There is another question. As you have discussed about the cancer treatment.
Yeah.
So we have chemotherapy, radiation, and hyperthermia, radiation therapy also, and hyperthermia. But in all the cases, the treatment does not work. So how do we do the same? Okay. So how do the cancer cell respond in these cases at nil temperature?
Sorry, how cancer cells?
How do the cancer cells respond in these cases at nil temperature? Sir, I repeat the question again.
Is different. Nil temperature is the temperature at which it loses its superparamagnetic nature. Here, what we have to do, actually, first thing about the treatment methods, there are different cancer treatment methods, but each method has its advantages as well as drawbacks. And we have, depending upon that, we have to select which method is suitable. In this method, again, it is in the developing stage. We have to work out for the materials which has very high SAR, very high specific absorption rate, so that with a very small amount, we can attain the desired temperature. At the same time, it must show some biocompatibility also. These are the requirements. Now, actual heat dissipation method is rotation, nil relaxation process. During that nil relaxation process, heat is dissipated. Just to overcome that barrier, when we reverse the direction of magnetic field, when we have to move them from easy axis to hard axis, we have to take energy. These nanoparticles take energy from the external AC magnetic field, overcomes that barrier. But when that barrier is overcome, it comes to the other easy axis, other side, by releasing the energy. So nil relaxation is responsible for release. Nil temperature is little bit different concept.
Okay, thank you very much, sir. If there is any question, please, you can type in the chat box or you can directly ask from the speaker.
So thank you very much.
So if there is no another question, so thank you very much, sir. Thank you for this nice lecture.
Thank you.
Thank you, sir, and very nice to see after 11 years. So you were there in NPL.
We have worked together for a few months. Thank you, Ashok ji. Okay, bye. And thank you, friends.
Hello. Yes, sir. It was
Vinod ji.
Yeah, Vinod sir is also there, sir.
Hello.
Hello.
Vinod Kumar, his mic is muted.
Yes, sir. Vinod sir. So Manoj Kumar Srivastava is also attending. He was in the Professor H.K. Singh lab.
Oh.
He's also attending this course. Now he's assistant professor and HOD of the department in Gorakhpur. I
remember all these fellow members: Anvir, Vinod Kumar, and Anu Rana ji.
Sir, Vinod sir is here. Vinod sir, please unmute yourself. Vinod sir, your mic is off.
Dr. Vinod Kumar, your mic is not unmuted. I think so. There is not audible.
Okay, thank you very much, sir.
See you again, Ashok ji. Thank you for giving me an opportunity to interact with all these fellow members. Thank you, all friends.
Yes, sir. Thank you very much, sir. So, dear participants, so now the second session of this today's second section is over. Now we will meet again at 2 p.m. So you are requested to join at 1:50 p.m. Next lecture we have from Professor Ashok Kumar Pundir, Department of Physics, Punjab University, Chandigarh. And the second lecture is on demonstration and working of sputtering unit. So thank you very much for listening all these two sessions with patience. Thank you very much, and we will meet at 1:50 p.m. Thank you to all.